Hello, everyone. My name is Tyler Ruggles. I would like to say a quick thank you to the MIT A+B Symposium organizers for their amazing effort to make this a successful virtual symposium. I'm going to share some recent work by Ken Caldera and myself conducted at the Carnegie Institution for Science titled Reliability and Generation Capacity in Electric Power Systems with Substantial Wind and Solar Power. There are many metrics of reliability in the power industry. One example relates power generation capacity and power demand or load. In this example figure, I'm showing an hourly load profile for 3 days in the ERCOT service territory in Texas. The maximum load value across all hours of 2019 is shown and is referred to as the peak load. The difference between the total power generation capacity and the peak load is referred to as the reserve margin. Here I've added an illustrative line indicating the total capacity. When used in a forecasting context, the reserve margin includes probabilistic components for both load and capacity, which I've indicated here by the shaded bands. Load forecasts can include projections of economic or demographic growth and probabilities of extreme weather events. Capacity forecasts can include the probabilities of unexpected outages and weather events as well. When using historical data to better understand these probabilistic distributions, the length of our data records will matter. Some regions may have more variability from year to year in their peak load values, indicating that we should consider more years when trying to draw conclusions from historical data. One thing you will notice about my cartoon total capacity line is that it is perfectly straight. This is representing more controllable generation sources such as gas, coal, nuclear, or large hydro. Intermittent and variable power sources like wind and solar PV are challenging to address in the reserve margin context because their production capacities change and cannot be relied upon to produce an exact quantity of power during peak load hours. With the idea of reserve margin in mind, let me tell you where we are headed. I will introduce residual load, which is increasingly used in contexts with large quantities of intermittent power, and I will demonstrate why residual load-based analyses will become increasingly informative as wind and solar PV generation expand. Additionally, we will analyze how peak residual load changes with increasing wind and solar generation. Last, we will analyze contributions to the probabilistic component of peak residual load with a specific emphasis on inter- and intra-annual variability. This work is important because better estimates of peak residual load and the leading sources contributing to the probabilistic distribution can lead to more informed choices for the needed dispatchable generation. This can help decrease capital costs for power systems while maintaining reliability. In this analysis, we will be using hourly load data from the ERCOT and PJM service territories, both with more than a decade of data. We use MIRA-2 satellite reanalysis data sets to calculate the hourly wind and solar availability during the hours concurrent with the load data. This preserves the correlations between weather and load, allowing us to understand resource availability during the peak load hours. The figures you see are for ERCOT. The left column shows the mean annual resource availability across the territory, with the sunniest regions towards New Mexico and the least solar availability towards the Gulf. The right column shows the most productive 25% of the territory. These most productive regions are the ones that we aggregate together and use to construct our hourly resource availability profiles or capacity factors. These profiles do not represent actual installed wind or solar PV facilities. As I alluded to earlier, generation capacity can be split into two groups. The dispatchable group contains systems whose power output can be adjusted and ramped up or down depending on needs. In general, the total dispatchable capacity can be illustrated as a straight line. Non-dispatchable technologies cannot be controlled and ramped up and down in the same way as dispatchable technologies. For example, solar panels produce power when it is sunny. In this figure, we have added an example contribution from solar PV that varies depending on the solar availability through that day. Because the power output from wind and solar PV are intermittent, estimating their contributions to peak load hours is difficult and involves some uncertainty. In general, The available generation capacity of wind and solar can be expressed as the installed capacity of that technology times a capacity factor. Different entities have differing approaches to estimating wind and solar capacity factors in their service territory. These different methods have historically worked in their regions. There is no single correct method. ERCOT, for example, considers the 20 peak load hours each year and averages over the previous 10 years for wind or the previous 3 years for solar to calculate the capacity factors. In contrast, PJM essentially selects a window from 2 to 6 p.m. each day between June 1st and August 31st for their calculation. With that in mind, let's consider a complementary approach which avoids the estimation of average capacity factors. Residual load, or net demand, is the system load after subtracting power contributions from non-dispatchable generation. Here, I've subtracted off the solar contributions from a fictitious solar farm. And now we're subtracting off the wind components. This results in a simulated residual load profile for these specific August days in the ERCOT territory. It is important to note that the hours of peak residual load may differ from the hours of peak load. In this example, you will see that the peak residual load hours each day are shifted later into the evening compared to the peak load values. We can combine the concept of reserve margins with residual load, where instead of analyzing peak load values to estimate the needed total generation capacity, we can analyze residual load values to estimate the needed dispatchable generation capacity. This will automatically take the correlations between weather, load, and resource availability into account. The figure on the right shows an example residual load profile based on 0 installed wind capacity and over 20 gigawatts of installed solar PV capacity. With that in mind, let's head back to our 17 years of hourly ERCOT load data, which are displayed on this figure. Even with this highly compressed x-axis, you will see there are annual patterns in the load values, but the details can be quite different. These 17 years of load data are affected by weather patterns, extreme weather events, and other factors such as economic growth. Any weather-induced extremes, such as heat waves, will also be represented by the MIRA-2 data used to derive the wind and solar hourly capacity factors. This long data record allows us to study both the inter- and intra-annual variability in the peak residual load. To account for the annual load growth, we normalize each calendar year of data based on the mean annual load value. This allows a better comparison of year-to-year fluctuations without the leading effects of economic and demographic change. The figure shows histograms of the normalized hourly load values where each line corresponds to a year of data. While the x-axis is labeled residual load, there is no wind or solar generation subtracted to make these specific profiles. To put these values in perspective, the mean ERCOT load in 2019 was 44 gigawatts, with a peak load value of almost 75 gigawatts. We borrow from ERCOT's peak load capacity factor estimation method and focus our attention on the 20 most critical hours per year. So instead of looking at the 20 peak load hours, we focus on the 20 peak residual load hours. The figure shows box plots of the peak residual load values per year on the left and all 340 values across the 17 years of data combined on the right. The orange line represents the mean value. These box plots help us visualize the actual hourly values and their spread. We will focus on 4 metrics. The first 2 are the mean of the 340 hourly values and the standard deviation. This figure shows a scenario with 0 wind and 0 solar PV contributing. In the following distributions, the wind and solar generation values will be incremented and they will indicate the fraction of the normalized load that they could supply. For example, a value of 25% solar generation could satisfy 25% of the annually normalized load. Curtailment is not taken into account. For any given resource scenario, the mean and standard deviation of the peak residual load values can help inform how much dispatchable generation capacity is needed to maintain a safe reserve margin. The standard deviation is only an approximation of the probabilistic distribution about the mean. We will focus on breaking the standard deviation into two additional metrics, the interannual variability, which we define as the standard deviation of the annual mean values, and the intraannual variability, defined as the mean of all of the annual standard deviations. The following progression of figures illustrates how the peak residual load values change with increasing wind and solar generation. We begin by incrementing the solar contributions. You will see that the first incremental solar contributions quickly reduce the peak residual load values, but after 10 to 15% of the annual load is supplied by solar, there are only minimal changes to the peak residual load values. This is because the peak residual load hours have shifted later into the evening when solar availability is low or zero. After reaching a 20% solar contribution, we begin to increment the wind contribution. In addition to the shifting box plots, you can see the four metrics listed above as well. The previous progression is helpful in visualizing how wind and solar PV impact the peak residual load values for specific wind and solar scenarios. We now take a more systematic approach that considers a spectrum of wind and solar scenarios. We will use 2D heat map figures where the x-axis indicates the annual wind generation as a percent of mean annual load, and the y-axis indicates the annual solar generation. The 0% wind, 0% solar scenario is found in the lower left corner of the figure. The 0% wind, 20% solar scenario is positioned vertically above the 0-0 scenario, while scenarios with wind will all be positioned rightwards. The following figures will focus on a single characteristic or metric of the peak residual load values from each year, such as the mean or the standard deviation or the inter or intra-annual variability. I will show the mean values next, but first let's look at the value we expect for the 0-0 scenario. If we look down here in the lower left corner, we can go up in mu total, and we expect a value of about 173. And that is exactly what we see in the lower left-hand corner, a value slightly larger than 170. The contour lines help show the rate of change of the mean value and confirm what we previously saw. Additions of solar up to approximately 10 to 15% yield substantial reductions in the mean peak values, while beyond that, the peak reductions due to increase in solar are minimal. Reductions from adding wind capacity are minimal when no solar is present, as you'll see along the bottom portion of the plot. And when there is substantial solar power in the system, the reductions in peak residual load due to wind show diminishing returns. This figure shows an estimate of the dispatchable capacity required to satisfy the mean value of these peak residual load hours. The PJM distribution is very similar and is not shown. The previous figure is heavily tied to the solar and wind availability during the peak residual load hours. The two figures you see here show the mean solar and wind capacity factors during the 20 peak residual load hours for each year. The solar capacity factor is highest when negligible solar generation is present. Wind is the same, with its highest capacity factors when negligible wind is installed in the system, and with the exception that the capacity factors are low for wind when no solar is present, as you'll see down here. We now switch to considering two components of the variability in peak residual load values. We begin by looking at the intra-annual variability. Again, this is defined as the mean of all of the annual standard deviation values. ERCOT is shown on the left and PJM on the right. In general, intra-annual variability increases with the addition of any wind or solar power. This means that for each year, the spread in the 20 peak residual load values for that year increases as wind and solar power are added. Interannual variability is a different story. ERCOT is shown on the left and PJM on the right. Interannual variability is defined as the standard deviation of all of the annual mean values. You will see that additions of wind power increase the variability for ERCOT and a bit for PJM. The more striking characteristic, however, comes from solar. The first additions of solar power for both regions decrease the interannual variability. For ERCOT, we see this decrease reverse after approximately 30% solar generation. Why is there a decrease? Both the ERCOT and PJM territories have peak loads correlated with cooling demand. The days with the most cooling demand in general are sunny summer days and naturally have high solar availability. More cloudy days with less solar availability will not experience as extreme of cooling loads. What these figures show is that solar PV can reduce the extreme load peaks on these outlier days that occur in a few years, and this makes the peak residual load values more similar year to year. This in turn reduces the interannual variability. It is also worth looking at how different the interannual variability values are between ERCOT and PJM. ERCOT appears to have much more predictable peak residual load values year to year. Therefore, if using historical data for analysis, it will be more important for PJM to consider longer data records with more years represented to confidently draw their conclusions. Society is striving towards a carbon neutral future with increasing wind and solar PV. From this work, we see that there will be substantial changes in the mean peak residual load values and their variability. This suggests there is a use for residual load-based methods to complement peak load-based methods for determining the needed dispatchable capacity for power systems. For the ERCOT and PJM regions, whose annual peak loads correlate with cooling demand, adding solar capacity will decrease the interannual variability of the peak residual load values. This makes the peak residual load more predictable and therefore the needed dispatchable generation more predictable year to year. We also show that in general, as wind and solar capacity increase, there are diminishing returns in reducing the peak residual load values and the needed dispatchable generation. With that, thank you for watching this video, and thank you to our colleagues David Farnham and Enrico Antonini for their assistance, as well as Gates Ventures and the Fund for Innovative Climate and Energy Research, who supported this work. I look forward to discussing this work with you during the symposium.